发声，就是这里，是这样 OK，大家。喂喂喂喂喂喂喂喂喂喂喂喂喂喂喂，好，谢谢谢谢谢谢。
然后我不知道今天会不会开始上课，所以
现在会开始，
因为隔壁教室现在是没有开的。
没有开啊？
对，老师你的卡应该可以开。
可以，对，开开看
那你要不要拿老师的卡去
，beep 一下。
对感应门禁就好了？那用我的
喂喂喂喂喂喂，hello hello hello。Okay, hello. Hello, 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 everybody. Yeah, so welcome to Introduction to DSP, Digital Signal Processing. Okay, so today is the first meeting of the class, and we supposedly we will open two classrooms, this one and the next one. Okay, so I explain. So my TAs, one of my TAs is going to check if she can enter the other room, and the plan is that for every lecture we will synchronize both classrooms using the equipment over here. So it has been working last year, so I'm pretty sure that we can do that again for this year. Okay, so for those of you that are standing behind, sorry for this. So for that, we are still handling that. So please just bear with me. It's okay to stand there, or if you want to sit down on the floor, it's okay to me too. 可以是不是 Okay, so yeah, you may please go to the other room. And let us know if you cannot hear me. Okay, there are an empty room in the next classroom, right? But otherwise, yeah. So any questions so far? Yeah. So let's wait for a while until our fellow classmates move to the other room. Yeah. Other room, please. Yeah. All right. Yeah. So hopefully, how are you today? How, yeah, 2025, right? So my name is Yiwen Liu, 我叫刘一问 and just a bit of an introduction of myself. I received my PhD in 2006 and from Stanford University, and my thesis is about audio watermarking. So signal processing really is my specialty. And since 15 years ago, I joined NTHU, and this is a list of all the courses I have taught. Okay, so as you can see, I have taught probability 4 times, linear algebra 5 times, and PDE and complex variable 3 times, and another PDE course with numerical method, I've taught that 2 times. And this is going to be my 5th time teaching Introduction to DSP. But other than that, I've also taught graduate level 研究所 graduate level DSP 7 times, and my own graduate level course called Analysis and Synthesis of Digital Audio Signals. I've taught that for more than 10 times, together with neural networks, and I've even taught computer programming for 1 time. All right, so this is about my teaching career to tell you. And so now let's spend some time to talk about requirement, suggestions, and how we are going to be graded, and so on and so forth. How we are going to organize our course for this semester. So first thing is about the size of class. So we do have a size. Currently, the enrollment is about 150 something. Okay, so definitely not. We cannot have everybody to sit in the same room. So that's why we need to meet at 2 rooms at the same time using synchronous broadcasting. And this room is going to be the main room, okay? And the other room as the overflow room, Lectures all will be recorded. Can we confirm that? Are we going to TAs? Yeah, TAs. Oh, yeah. Are we going to record every lecture? Right? Yeah. Yeah. So lectures will be. I just confirmed. The lectures will all be recorded, and video will be provided after class. Okay. So that being said, what is the meaning of having 2 rooms? So the main room. In the main room, I have 1 requirement. Okay. In the main room, I require that please do not bring food into the classroom. No eating. Drinks, I'm fine. Okay. But please don't bring anything that's too delicious, because it's going to be a distraction for me and for others. Okay. If you really need to eat your lunch, I understand that we have a lot of students on campus, and typically you don't have enough time to have lunch, right? And this is the first class after lunch hour. So if you really need to eat, go to the other room. Okay. Can we agree on that? Yeah. If you really need to, you're really hungry, you really need to eat, go to the other room. Okay. So this is the main room. The other room is the overflow room, and in this semester, I plan to teach with a mixture of PowerPoint and Blackboard. I'm going to use both, right? And pre-notes, basically handout. Handout will be provided. I promise it will be available beforehand. For this semester, I'm going to create the handout. If you know, last year we didn't do that. Last year is purely teaching from iPad. But this year I'm going to try PowerPoint and Blackboard. Okay. And what are the prerequisites for this course? DSP has a lot to do with math. Yeah. And you need to be comfortable with calculus and complex numbers in particular. Complex number, x plus y, iy. Okay. Complex numbers. And if you are from our College of ECS, the prerequisite really is signals and systems. That's another course, a kind of a foundation for DSP. So if you have taken signals and systems, you will be fine. Okay, you can continue with this course. But in case you haven't, so how can you tell you have taken signals and systems or equivalent? So I suggest that you can ask yourself, Am I familiar with Z transform? Do I know convolution? Do I know what is a delta function? Yes, delta function, right? And do I know Fourier transform in general? Okay. So if the answer is yes, you are going to be okay, right? But if the answer is no, then so I've told you that this is a prerequisite. Okay. We are going to build upon this concept when we learn DSP. Okay, is that clear? Z transform, convolution, Fourier transform, and generally complex numbers, delta function, things like these. Okay. So, but with that, let's talk a bit about DSP now, right? So, if C stands for continuous, D stands for discrete. So the overall workflow for DSP is going to be like this graph. Okay. On the very far left, we have the input signal, which is continuous as a function of time, a continuous time variable t. Okay, continuous time t. And we explained that we recommend that the signal needs to first go through an analog filter that is called anti-aliasing filter. Okay, after that, the signal is still in continuous time, but then we convert it from continuous to discrete time using some kind of sampling period t. Okay, sampling period. We'll explain that in a moment. But then after that, things become a sequence of number, x of n. N is basically integer, 1, 2, 3, 4, 5. Okay, n is integer. And then in this discrete time domain, we will process the signal using this equation only. Okay, so it's like if you need to know enough to ignore DSP, 知道够多可以忽略. If you don't need to know enough to ignore DSP, I'm going to tell you that share with you that the only equation you need to really master is this difference equation. 这是一个差分方式. It's a difference equation, right? So if we read the details of this equation, and we're going to encounter this a lot and a lot, right? So let me explain. So let's say if x is our input signal and y is what this equation produces, the output. Okay? So we are going to express the output as a linear combination of the input signal, linear combination, as well as the output signal itself in the past samples. Okay? Looking backward in time. Okay? So this is what a difference equation is, and is going to be applied almost always for DSP. Okay? Nothing more than this. So almost during the entire semester, I'm going to say at least 70% of the time, we are going to study about this equation. How do we use it to process our signal? So we have the input, we have the output, we are processing a signal. So far, so good. Input, output, processing. We're going to process the signal in the discrete time domain. And then after that, our signal has to come back to the real world. So it needs to be converted from discrete time back to continuous time, D to C conversion, with the same sampling period, and so that the output that we can transmit, or you can listen to, we can watch, we can, so the output for the entire system will go back to the continuous time domain with the variable t as a function of t. Okay, so that's sort of the overall flow chart for DSP, digital signal processing. And along the way, you will learn the concept of going to frequency domain. Okay, we're going to do a lot of frequency domain discussion. So we'll review the continuous time Fourier transform, FT Fourier transform, with this expression where you have an input signal in the time domain. We are going to convert it, to transform that input signal to a spectrum, the corresponding spectrum in the frequency domain, with a variable big omega here denoting the frequency. Okay, so that's a continuous time Fourier transform. And it also has a discrete time version that we call discrete time Fourier transform, DTFT. Okay, it looks like this. We will come to this notation many times. And they are going to be useful. So you can use discrete time Fourier transform to characterize a system as well as to represent the signal. So we'll cover that a lot. But in addition to these two different versions of Fourier transform, we have a few more versions. So there's the discrete FT. And its fast implementation is what is called the FFT, Okay, we'll be doing that too, and as well as the notion of short-time Fourier transform to transform a one-dimensional signal into two-dimensional onto the time frequency plane. That can be done. So we will, along the way, we'll encounter different versions of Fourier transform, and they are going to be very useful. So next, I'd like to show you a brief plan for this semester. We are going, first of all, we are going to use, I'm going to suggest this book as the textbook. 课本. Oppenheim, Schaefer, both MIT professors, and this book is now in its third edition. The title of the book is just called Discrete-time Signal Processing. Okay, so check it out. And frankly, I'm not going to teach. This is an introduction course, so we are not going to cover everything in this very pretty thick book. But I highly recommend you to get a copy of the textbook because it's used globally as the most important reference for DSP. Okay, so even if you don't obtain a hard copy, you might be able to. You may want to check out if there is any electronic copy available on the internet or something. So there is a third edition which is not different, which is not that different to the second edition. 第二版 or 第三版, not so different. So I don't mind if you get a second edition somewhere, electronic copy. But this book is highly regarded in the field, so I highly recommend that you get a copy. But otherwise, we are going to selectively focus on only 3 chapters. Chapter 4, Chapter 5, and Chapter 7 of the textbook, while we also touch a bit on Chapter 8 to 10, if time permits. We'll cover like the middle part of the textbook, selectively cover on different topics. So we are not going to, I promise you, we are not going to like cover the entire, every single section of the chapter. That's not what we are going to do. And I will explain the reason in a moment. Yeah. We are just going to be selectively covering important concepts from the book, while you can keep the book as your own reference. Yeah. 这样可以吗? So far so good? Yeah. And also in this semester, as well as last year, we meet every week on Wednesdays and Thursdays, right? So Wednesday will be today, 2 hours, Thursday for 1 hour. So I'm going to format the meetings into Wednesday lectures and Thursday discussions, okay? So on any regular Wednesday when we meet, I give 2 hours of lectures. So starting next week on Thursday, okay? Tomorrow I'm still going to give a lecture because it's just the beginning of the semester. It makes no sense to start discussion, right? So I'll give 3 hours of lecture, including right now for this week. But next week, starting next week on February 27th, we will alternate between 2 kinds of discussion sessions, okay? The first kind is called what I call follow-up discussion, or FUD, okay? Follow-up. So, and the other kind is just discussing the homework, right? 2 kinds of discussions on Thursday. Every other week, we'll alternate between follow-up and homework discussion. And then, even though this course is officially offered in English, and my lectures are all going to be English, and I know that we have international students among us, right? So I'm going to almost entirely teach in English. But for the Thursday discussion, I feel that actually it worked last year. It worked pretty well. So we are going to offer 2 sessions, same content, 2 sessions. And 1 session is in English, and the other session following the first session will be in Mandarin. Okay, so please feel free to attend either one or both. Yeah, but either one. It's going to be the same discussion, same questions for discussion. But this second session is going to be offered, to be conducted in Mandarin, in our native tongue. Okay, so feel free to either attend in 英文 or 中文, English or Mandarin. All right. Any questions so far regarding the format, the course plan? Please choose one to attend. Okay, English or Mandarin for Thursdays. And here comes the tentative syllabus, the plan for the entire semester. And you can follow this link. So the PowerPoint has been uploaded to EE class Okay, so it's available for you to download, but otherwise, this is a tiny URL, NTHU DSP-2025. So I'm going to, this is a Google Sheet, all right? So I'm going to update this Google Sheet constantly. So, but the current plan is that we're going to spend 3 weeks on chapter 4, 3 weeks on chapter 5, and there will be the only one and only midterm over there on the 7th week. And after that, we spend more time on chapter 7, which is the core of this semester. And in chapter 7, it's all about design, okay? Design, design, design. IIR, FIR names for different filters. Impulse, IIR is infinite impulse response, FIR, finite impulse response. So we'll teach you how to design filters, basically, for chapter 7. But before that, we need some kind of background, the foundation knowledge. Okay? Before we design filters, we need to know how to analyze a filter. Okay, so chapter 5 is about analysis, to analyze the filter if it's given to you. And then starting chapter 7, we talk about how to design a filter by yourself. Okay? Yeah. And there are different kinds and different methods. And then after that, this is quite new, something new I want to try with you. So in May, in the 3rd month of this semester, I'm going to try to offer to you two special topics. The first special topic is adaptive systems. Adaptive systems. And so filters can be made adaptive. So they change their parameters while being used, while they're being used. And that's a very important concept, adaptive systems. And it has something to do, it can be regarded as the prototype. A prototype of what? A prototype of neural networks. We know neural networks can be trained, right? So actually, you can think of neural network as a nonlinear adaptive system, right? So it's important, like nowadays, to go back to this very topic and talk about and I'm going to share you a few things about adaptive systems, adaptive filters. So there might also be homework related to that. So this is the first special topic. And the second special topic is what I call transform-based information retrieval. Right? Information retrieval. Remember, I just shared with you that signal processing is about having an input and having an output, right? Input is a signal, the output, right? After the chain of actions, the output is also a signal. That's sort of a conventional way, traditional way of thinking about signal processing. But now, more and more, signal processing is sometimes, in certain applications, a signal processing system simply does not produce an output. Or that's probably not fair to say. Sometimes a signal processing system does not produce a signal as the output. But instead, the system can extract information from a signal. For example, I'm now talking, right? A speech recognizer as a signal processing system, does it produce a speech output? Mostly not. It produces text output. We call that speech to text conversion, right? So it's about retrieving information from signals. So that's a hot topic. So in the end of the semester, I plan to share with you a few things that I know about speech processing. How do we analyze the content of speech using Fourier transform? Transform-based information retrieval. So that's the kind of plan for the last part of this semester before we have a final exam on the very last week of the semester on June the 4th. Right? Any question regarding to this plan? Does it look good? Looking good? Looking good? Looking good? All right, so let's try our best to stick to this plan, right? And now on this slide, I want to share with you a plan on how we are going to give you grades for Thursday's participation, right? So the participation will account for 6% of your final grade, okay? As that's the same as last year. So same as last year, you will earn 2% or 2 points for each stage appearance. So the way we're going to discuss, this is a large class, right? So we cannot possibly break you into smaller groups. So instead, we are going to invite you. We're going to have you sign up. I'll explain. So each time when you're going to come up, you're going to sign up and volunteer to come up in front of the blackboard to explain your solution. So that's the plan. Okay, and for each stage appearing on the stage, okay, this is the stage. For each sign up and appearance on the stage, you get 2 extra points. I mean 2%, 2 points for each stage appearance. But I also encourage everybody to ask questions. Okay, question your fellow students. No, yeah. Please don't take it personally. We all need to learn how to accept criticism and offer criticism, right? So in each session, it's not necessarily a criticism, but you will anyway learn one. You will earn 1 point if you ask a question, any kind of question, right? Or make comments or make suggestions on others' solution on the board. Sometimes the same question have different solutions, right? You may, after this one person show their solution on the blackboard, you might feel that some parts you can disagree, or you can offer a different angle. So that's the chance for you to, if you just raise a question, I will ask you if you have does anybody have a question? And if so, just please raise your hand, and I will invite you to talk. Okay. So for each time you do that, you will earn in each session. If you do that, you will earn 1 point. 1 point per session, not 1 point per question. Okay. Please do not ask 10 questions and expect to get 10 points. Right. 1 point per session. We want everybody to have as much chance as possible. All right. So 2 points for stage appearance, 1 point for offering a question. Okay, so that's the plan. So I calculated that there will be 12 discussion sessions. And if we have 10 people on stage every Thursday, then we have a total of 120 opportunities to earn 2%. Okay, so that's a quick calculation. And last year, about 2/3 of all the students. Last year we had 156 students. 99 of them eventually earned something from Thursday. So that being said, about 57 of them remained silent. Okay, that's okay too, but it's up to you, right? About 2/3 of students last year scored at least 1 point, and 44 of them scored all 6 points. Okay, so that's just some simple statistics, and we'll see how things work out for this year with you all. Okay, yeah. So that's a bit from last year, and that's my plan. And to enable discussion, the TAs will open the link for sign-ups every week. Okay, please do that. Open the link, and then if multiple people, you will share your solution on stage. But if too many people sign up for the same question, that happens a lot sometimes, then we have to make a random selection. So inevitably, 无可避免, we will have to make random selection, and the selection will be based on this kind of this principle that we will give higher priority to those who haven't showed up on stage. Okay, please give, if you are very outgoing and you want to sign up every session, well, chances are sometimes you need to yield. We want to select to give those who haven't showed up on the stage every week, they get the highest priority. Okay. Hopefully we enable more and more students to get a chance to stand up here and talk about your solution. Okay, so this is my plan for last year, and this was my plan for last year, and this is also going to be the plan for this year. Okay, any question regarding this arrangement? Any question? Last year, in the end of the semester, I received one complaint. Okay, a student sent me an email complaining about this arrangement, and he told me that this is unfair. because he is an introvert. I think he does not feel comfortable standing up on the stage. So from the beginning, he plans to not sign up and just do his best in the exams, right? So, I replied to him that your message is well received, but I feel that nowadays, even if you're an introvert, please please try not to be afraid of talking in public, right? We want to kind of foster a friendly environment, okay? So in every question we offer it in friendly ways, okay? So please do not laugh at others, or when you offer a question, we interact, it's okay to make mistakes. We are all human beings, right? So it's okay to show a wrong answer. You still earn 2 points, okay? If your answer is wrong, which is good. If your answer is wrong, then most likely you do not copy it from the internet, right? You might have come up with your own ideas. So that's great. So please try not to be shy. Please not to be don't be too shy. Okay. So, but otherwise, that's my reply for the student. I was sorry, but we have specified the rules from the beginning of the semester, right? So there's no way I'm going to reconsider his grade. Okay. So 6 points over here, not too much, but I think 6 is a good number. Yeah, 6 points is a good number. Right? Any question regarding this plan? So what are the questions from last year? So in here I give you a few examples. So we started this way of class meeting in 3 years ago. Okay, 3 years ago we started follow-up discussion, FUD. So this is a sample question, which reads like proof of a theorem, and there's assumption, and there's definition. You prove this equation, and you want to show something, and blah blah blah. So that's kind of the level of difficulty for the follow-up discussion questions. Okay. In another sample question, we asked you to read something from Wikipedia, and then construct an example which converges only at z equals 0. Anyway, so these are the kind of questions we are going to offer to you in this semester, right? Follow-up discussion. And then next, I'm going to talk about homework requirement. So we will have 5 homework assignments, and they account to 25% of your score. And the homeworks will mainly be handwritten problems, associated handwritten problems. And one of the purposes is to facilitate your preparation for exams, for midterm, for the final, because both exams are going to be written tests, right? So you need to be prepared. So that's one main purpose of doing your homework, right? Working on your homework, but other than that, on top of that, some of the problems will involve running a MATLAB program and summarizing what you observe. Okay, so these homeworks are not going to be really computer homeworks, because I don't require you to write your own code. Of course, you can feel free to modify my source code, but I'll offer my source code to you for you to just run it in MATLAB. MATLAB is very super convenient for signal processing. Okay, I like it, so I love MATLAB. Love MATLAB. You hear me? I love it. So they're not really computer homework, but they allow you to familiarize with the MATLAB environment, and which is particularly good for signal processing. Okay, so I'll give you some example code, and you'll run it and just summarize what you observe. This is signal processing is like doing an experiment. So we give you the source code, you do the experiment, okay, and tell us what you think. Tell us what you observe, okay? So the homework will consist of mainly the written part, as well as also written part, kind of you need to report on on your observation. And for the handwritten part, of the homework, we will always openly discuss all the questions on Thursday, okay? Before each homework is due on Friday. Okay? Friday homework due, Thursday we discuss the homework. The Thursday before every homework is due, we will discuss it right here in this classroom, right? So the point is that the homework is not supposed to fail you. We want everybody to get nearly full score for every homework. Okay? The homework is not supposed to fail you, and more interestingly, we will not rigorously check on plagiarism. 抄袭啊, we will not check you rigorously. Last year, I simply said we will not check you. Okay. It's not like that we encourage you to plagiarize. No, that's not the concept. But the point is that now, there's so many AI tools, and our homework questions are not going to be so smart that nobody else has ever thought of in the world, right? So highly likely, if you post my homework questions on the web, or ask ChatGPT or Gemini or what, DeepSeek, they will answer, give you the answer in 10 seconds. Right? Okay, so I figure that now it's meaningless to check plagiarism. So instead, I want to encourage you that homework is your work. It depends on how serious you are. Right? If you're serious about something, you try to work it out on your own, right? If you're serious about something. But if you're not so serious about DSP, then yeah, it's up to you, right? This is you're all grown up, right? Yeah, so 都已经成年人了. So we are not going to check you on plagiarism rigorously, but please, if you are serious, try to work out the homework solution on your own, okay? And if there's any difficulty, let me mention that therefore, no late homework allowed. Okay, please do not. Well, by 15 minutes, that's fine, but late by 2 days, probably not acceptable, right? If you're late by 5 minutes, just miss the deadline. That's fine. Send an email to me. I'll just take it, right? But in principle, no late homework allowed. No, we don't allow. We are not going to allow late homework. And the idea is that this sentence, done is better than perfect, right? If you need help, please seek help earlier rather than later. Our TAs are there to help you. Okay, so TAs, ask the TAs to offer TA hours, okay, before the homework. All right? Are we good with this? Can we agree on this? Any question regarding homework requirement, plagiarism? So here's an example of computer exercise from last year. My own field is audio processing. So some of the problems, the computer problems, will ask you to listen to the results of signal processing. And below is one example. So you may read a file, an audio file, and then figure out the waveform and the sampling rate. And then you're going to, last year, they changed the sampling rate and listen to the result. Changing the sampling rate, okay? And using resample, using such kind of function. So that's one example of computer exercise. And now the next thing I need to mention is the grading policy. So the plan is to sum of 4 components. The midterm is, no, not midterm 1, only one midterm. Right? There's going to be only one midterm. So that midterm will be 30%, final will be 40%, homework will be 25%, and Thursday participation will be 6%. If you add them up, it's 101 point. Okay. Yeah. So is that clear? Yeah. And so if that's clear, let me also mention that I will remind you that for the final and midterm exams, you are allowed to bring in an A4 size cheat sheet, and you can write on both sides. Okay? Only writing, no printing. Okay, no miniature printing. 不能微缩在影印啊。No 3D, right? Only 2D, double-sided. No Mobius strip, Mobius. No, nothing funny. Right? A4 size cheat sheet. You can write on both sides, right? And your final letter grade will not necessarily. Let me mention this. Okay, after we sum up with this proportion, you get a number G, right? Called the sum of your grades. And we do not promise you that your final letter grade, the university uses the letter grade system, right? But we cannot promise you that your letter grade will be direct number to letter conversion. We do not promise you that if you score G of 90 points and above, you will get an A+. We cannot promise you that. Yeah. But we also will not promise you that if you get something below 60, you fail. No, we don't promise either way. Yeah, understand? There will be no direct conversion from your G score to the letter grade. Okay? But instead, what we promise is that we will preserve the ranking. What does that mean? A person with a higher G will not get a lower letter grade. That's our principle. Okay? You get a higher G, then another fellow student, you get a equal or higher grade, letter grade, compared to that person, compared to your friend. Is that clear? Yeah. We preserve the ranking. And our teaching team will reserve the right to determine the grade boundaries. The grade boundary. What's the boundary between A and A+? What's the boundary between B+ and A-? We reserve the right to determine the grade boundaries. Any question? Yeah, so this could be problematic. Perhaps? Are we good with this? We preserve the ranking, and we will determine the grade boundaries. Okay? Yeah. I typically look for a gap. Yeah, if there is a gap, then I break it over there. So that's almost entirely up to me. Is that okay? Let me just say this in advance, right? The grade boundaries will be, the right to determine the grade boundaries will be reserved by the teaching team, including myself and the TAs, right? Typically, I give A+ to 10% of a class. Last year, maybe 12%, but no more than that, okay? In my personal sort of habit, 我的习惯, yeah, I think A+ should be rare, should be scarce, okay? We cannot give like 40% of everybody A+. I think that's too much, right? So typically, in the past of my 15 years of teaching career, I usually give A+ to top 10%. Okay. All right. So that's the plan. That's my rule. Yeah. Next thing is about. Let me officially introduce our TAs. So we have 4 TAs this year, standing behind in the back of the classroom. That's Lin Ziqi. That's Ziqi. Okay. And then in front here we have Wendy, Yu Nianheng. Say hi, Wendy. And where is Jason? Jason, is he in the other room? Yeah. And there are 2 boys and 2 girls. Jason and Yongyue are 2 guys and 2 girls. Yeah. So that's our teaching team. And TA, I ask you to please announce your TA hours. You guys should discuss within yourself. Yeah. And they are going to mainly help you with homework. Okay. And one more thing about homework. Homework can be submitted through the university EE class system. Right. For those of you that are NTHU students, you already have an account, right? But in case we have, I think we do have a few exchange students as well as, I don't know, maybe students from other universities. Please talk to us if you don't know, if you don't have an account yet. We'll help you arrange that. But otherwise, last year, everybody submitted homework through the system. No hard copy. Just scan your homework, okay, into PDF. Yeah, that's how things worked last year. Right. Any question regarding this slide? Okay, so to summarize, this course, I think it will really interest you if you want to learn Fourier analysis and filter design. Okay? It should also be helpful to you if your work, if you in your future or your current project, you have a project with time domain signals. Okay, if you work on time domain signals, signal that changes in time, then this course should be helpful. And the application could be plenty. So we have applications in communication, multimedia, any virtual reality, augmented reality, biomed, remote sensing, anything, stock market, anything that changes in time, global climate, can be viewed as a signal. And we can process the signal, or we can extract information, right? So applications are plenty, and we teach also a bit about machine learning in the end of the semester when we talk about adaptive filtering as well as information retrieval. And let me also mention that there are quite a few related courses on campus, not necessarily offered in this semester, please, but please, if you're interested, you may as well consider taking the graduate level DSP directly, especially if you are a fourth year student, if you are happen to be staying for your graduate school, if you already know that, then there's an advantage of taking the graduate level DSP directly, because then you can that can be counted toward your graduate requirement, your graduate school requirement. So please consider that. If you are a fourth year student, please consider that. And this year, the DSP is going to be offered by Professor Lin Jiawen, who is an IEEE fellow in signal processing. Right? Okay. And another fellow of IEEE, Professor Wang Jinliang, he has been offering adaptive signal processing. So if you get interested, you may consider taking this as an advanced level, a follow-up. Okay, adaptive signal processing, as well as if you're interested in audio acoustics, there's me, as well as Professor Bai Mingshen in the Power Mechanical Engineering Department, Dongji Professor Bai Mingshen, who is a fellow of who's also a fellow, and a future fellow. Professor Li Qijun specializes in speech as well as other things. So you may consider taking speech signal processing, another graduate level course. And I think it's also offered this semester. Right? So keep in mind, there are different choices: video, image, biomedical imaging, as well as a signal processing IC design, which is Professor Huang Yuanhao's specialty. Right? Yeah. So quite a lot of courses to take, but this course hopefully will serve you well as an introduction to DSP. Any question, please, regarding this welcome message? Any question? Are we good? Are you okay? Yeah. So let's maybe take a 10-minute break. So after the break, I'll start my first lecture, right? 10分钟，好。哦，好。哎，
那个我们上学期我有跟你聊过，我想要再询问一下，现在还有那个音乐创作小。
Hello. Yeah. We should play some music during the break. In the past, in my course, I asked my TA to play music. Yeah, during the break. Okay, but anyway, all right. So thanks for sticking with me for this second hour. And in this hour, starting this hour, right now, we are going to talk about the first topic, that is to sample a signal. Sample being a verb. Okay, to sample a signal. To sample a signal from discrete time, from continuous time to discrete time. Okay, so we talk about discrete time sampling of continuous signals. All right, so yeah, not too familiar with this interface. So we'll talk about two topics, all right? So first, we'll tell you the definition of sampling in the time domain. It happens in time, all right? Everything happens in time. But then we talk about the effect of the equivalent effect that created. This action of sampling creates some effect in the frequency domain. And we talk about that. Yeah. So sampling in the time domain, first thing first, let's look at this diagram, this very simple diagram. Okay, let's look at the diagram. So on the left, we have a signal. Okay, as a function of time, t being the time, and the unit might be second. Okay, time happens continuously, and let's denote a continuous time signal as x sub c. Okay, x sub c. C stands for continuous. Okay, C stands for continuous. And then we have this box that we denote as C/D, C to D conversion, okay? Continuous to discrete conversion. Okay? Continuous time before and discrete time after the conversion. And with that, in this, we need to specify a sampling period that's denoted as T, okay, sampling period T. So the key idea is really just this equation. Okay, there's one equation right there, x. Now we look at the continuous time signal at nt, right? N is 1, 2, 3, 4, 5. Okay, and t is a constant. The sampling period is a constant. Okay, for example, 125 microsecond or something like that. T is a constant. Right? T is a constant. So what this equation means is that we will look at our signal. We look at our signal at integer multiple of t, 1t, 2t, 3t, and so on. And also in the time can go backward, 0t minus 1t minus 2t. Integer multiple, 整数倍数的, integer multiple of the sampling period t. So that's the moment we look at our signal. And then we look at the signal quickly and we record the result and call them x of n as a sequence of numbers. Sequence of numbers, right? 数列. The result of discrete time sampling is a sequence of number denoted as x of n. So far so good? So that's the notation. So this is a system diagram of continuous to discrete time convergence, C to D. T being the sampling period, n is integers, right? N is an integer. And I have one remark, okay? So this course is called what? What's the name of this course? What processing? Digital signal processing, right? But somehow here we cannot yet, I say that x of n, this signal, discrete time, for sure, cannot yet be called digital. Not a digital signal yet. Okay? And the reason is because x is still a real number, any real number, which might be irrational, 无理数, right? So we know that a computer, when we use a computer to store and process a number, the number has to be represented binarily. 要有二进位, binary. You need to use some kind of binary representation system to decode, to encode our number. And that hasn't happened yet. So this is just about sampling, looking, measuring the signal, taking a measurement of a signal at this moment, at every integer multiple sampling period. Okay, so not yet digital. We do not represent the numbers binarily in a binary representation yet. Okay, so by definition, this is not yet digital, But we will come back to that. We will come back to this topic when we discuss quantization. That's how we round up our number, and so that the number is ready to be stored and processed by computers. Okay, we come back to this topic. But in the next hour, we will just stick with this discrete time notation, and we think of a discrete time signal as a sequence of numbers. Okay, sequence of numbers with an index n being integer. So now we have a question. But let me, before I ask the question, let me just draw, let's try to make a sketch of what's going on, right? Let's make a sketch. Suppose that we do have a signal like that in the time, okay? And this is our time axis, happens forward. And this is a continuous time signal that we denote as x sub c of t. So sampling really means that we are going to measure our signal at integer multiple of the sampling period, 0, 1t, 2t, 3t, and so on. So here, like the spacing in between points is the sampling period, okay? Which, for example, as I said, might be 125 microsecond, something like that, a sampling period. So as a result of sampling, we are going to look at our signal right here. It's so high. We may even have a vertical axis, right? Any continuous time signal may have a unit. The unit might be, let's say, millivolt, right? The unit might be millivolt or any other physical quantity. So we take a look at our signal at 0t, and then again at 1t, and again at 2t, and 3t, and so on, and so forth. Yeah. So that's the idea, kind of a sketch of what's going on when we convert a signal from continuous time to discrete time. Okay, continuous time 连续, discrete time 离散. So that's a sketch. But now let me ask a question. Let's ask the question together. We need to wonder if C to D being a conversion, if the conversion, whether or not the conversion is invertible. 是可逆的吗? Is the conversion invertible? That's being said, what we mean is that when we convert the continuous time signal to a sequence of number, can the process go back? Can we reconstruct the signal out of its samples? If what we know is all about only discrete time samples, can we synthesize the signal back in the continuous time? That's the question. Is C to D conversion, is it invertible? Is this process invertible? Does the inverse exist? Does the inverse exist? Okay. Because this is an important question, because if it exists, then we can have a D to C conversion, right? C to D, and we can very well call the inverse D to C, right? C to D first, and then D to C, right? But really, is any signal, is a sampling of a signal invertible? And the general answer is no. The general answer is no. C to D conversion, continuous to discrete time conversion, is generally not invertible because of an effect called aliasing, right? So I'm going to explain to you. So that is to say that it is possible that we have two different signals, x1 not equal to x2, okay? It's possible to have two different signals that become identical, 变成一样啊. They can become identical after sampling, in that at every moment nt, the equality happens to hold. It's possible, right? It's possible for any integer multiple of t. Okay, it is possible that in this signal we have these samples at nt, but you may as well have another signal. It's possible that we have another signal that happens to equal to our signal at every moment of nt, but in fact they are different. So what do I mean? So it's possible to have another signal that happens to go through this point and then deviate and then go through this point again and then making its detour and go crazy. And as long as it's a continuous time function, right? It's possible to encounter such situation theoretically, right? So this is just to explain to you that it's possible that we have two different signals that become identical, 变成一样啊, become identical after sampling, right? Theoretically, it's possible, right? So theoretically, mathematically speaking, C to D conversion is not invertible in the most general sense. It's a many-to-one mapping, right? As a function, right? It's a many-to-one mapping. So that's an important concept. And here is another plot, okay? Another example, a kind of a good example for aliasing. So let's say we have the red. The red line is a periodic signal, a sine wave, if you will. So that it happens, it just goes up and down all the time, right? And let's say we are going to sample this signal with a t of something. T of 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. It looks like my t, my sampling period is 1/8, 1/8嘛, So in this example, we have, in that example, we have t equals to 1/8, if you will. And the result is marked as circles, okay? The circles tell you the result of sampling with this sampling period. So first, it crosses right here, and the next moment, next moment, next moment, and so on and so forth. Okay. So is this a valid action of sampling? Is this valid? Sure, of course it's valid. We are going to measure our signal every so often, every integer multiple of the sampling period, which is 1/8. Okay. So of course this is a sampling, There's nothing wrong in here. Yeah. But what is wrong is that if you just pretend that you don't see the red, okay? Let's pretend that we only see the result of sampling, which are the circles, right? What can you tell? If you only look at the circles, are you going to think that the underlying signal is the red one, which has a much higher frequency? At least appearing to by inspection, 用看的, By eyeballing this example, will you say that, okay, I'm looking at the circles, and the underlying the signal, the corresponding continuous time signal must be this red one? Yeah, it's not so likely. It's not the most natural way to look at your result of sampling and say and conclude, 下一个这样结论, and conclude that, well, our signal in analog is the red one, which fluctuates at a much higher frequency. Okay. Instead, what is more natural? Okay, anybody tell me what is more natural? Of course, this is like roughly speaking. Okay. The more natural way to look at the circle is to interpret it as a result of sampling a signal that varies more slowly, like that. Right. That's a more natural interpretation. Okay, that's more natural. Yeah. So this is just to tell you that two different signals. This red one, as well as the one that I'm drawing right now, as well as this one, these two different signals can happen to share the same result after sampling. Okay, so there's ambiguity. There's ambiguity in looking at the result of sampling. In the most general sense, sampling is not invertible. Okay? Sampling, in the most general sense, is not invertible. And this ambiguity is what we call aliasing. Okay? Sometimes a high frequency, we come back to that. When sometimes a high frequency component can disguise itself. Okay, 伪装啊, can be disguised as a low frequency signal after sampling. Okay, so there's ambiguity in that. So far so good? Yeah, aliasing. Typically, aliasing is something to avoid, and we will talk about that. Okay, we don't want this to happen. So, but unfortunately, if it happens, then there's no way we can tell whether the signal is high frequency or low frequency after sampling. There is ambiguity. So the next better thing that we can assume we can possibly assume is that, however, we step back and require the signal to have this property. What property? If we require our signal to be band limited, okay? So in this handout, every time I introduce a new term, new terminology, I use italic. 我用斜体啊. Every time you see an italic word, that's a new terminology. So this is to step. So if we step back and require our signal to be band limited, that being said, that means if the bandwidth of the signal is finite, then turns out that it becomes possible. It becomes possible to reconstruct the signal from its samples. It becomes possible to reconstruct the continuous time signal from the result of sampling if we assume that the signal is band limited, if the signal has a finite bandwidth in the frequency domain, okay? If that assumption can be made, then it is possible, it becomes possible, roughly speaking, to reconstruct, to make the reconstruction from its discrete time samples. And just jumping to conclusion, directly, we say that we require the sampling, and how can we make sure this happens? We will require the sample. We need to require the sampling frequency. Sampling frequency is defined as 1 divided by t, 1 over t. Okay, 1 over t. So as an example, if t is again 125 microsecond, I mean, then f under this definition, that's a definition of sampling rate. F sub S stands for sampling, okay? Sampling frequency or sampling rate. Being 1 over t, so if we do a quick calculation, then the result is what? 8 kilohertz, if I understand correctly. Something like that, okay? Sampling frequency has a unit of hertz, right? Sampling time, sampling frequency. So just long story short, roughly speaking, the conclusion turns out to be that we should require the sampling frequency to be higher than 2 times the bandwidth of our signal. You're interested in a signal which has a bandwidth of B. Make your sampling frequency at least 2 times higher. So that's a recommendation. That's kind of a universal recommendation. Yeah. Jumping to a conclusion first. But why that's the case, we will go through the derivation next, okay? But that's the conclusion, sampling rate. We recommend it to be set at least 2 times higher than the bandwidth, 2 times broader. Yeah. So far so good? Yeah. So that's just to summarize. Now we have introduced a time domain definition of sampling, which is we have a continuous time signal. We go through a C to D converter, and the result is x of n, and with a sampling rate, sampling period t, and just please memorize that xn is defined as x of c, the continuous time signal sampled as integer multiple of t. That's a definition. That's a sort of a definition. Okay. So that's what's happening in the time domain. But next, let's talk about the effect in the frequency domain, right? Yeah. Talk about the effects in the frequency domain. And now we need to introduce a few variables, okay? So let's first define kind of a strange thing that I denote as S, right? We'll come to that, yeah. So let's make a few definitions. Let's first define S like that, being a summation from minus infinity to infinity delta function, okay? Delta function shifted to the right or to the left by integer multiple of t, okay? And we sum them up. So let me draw a picture, yeah. If you have your iPad, you can also write on the note. So the room is supposed to be left blank here for you to take notes. Okay. So let's make a sketch. S of t. What does S of t look like? It's a summation of delta function, right? Okay. So We know that delta function is typically sketched as using an arrow pointing up, right? An arrow pointing up representing a delta function. This is delta t, being infinity at time 0, right? Delta t is defined as being infinity at time 0 and 0 elsewhere. Just to review, such that you take the integral of delta t with respect to time, then you get unity. Okay, that's a definition. That's sort of that is what delta t represents. Yeah, it's a generalized function. All right, so we have delta t, but that's just one component. We have an infinite series of delta t shifted to the right and to the left, right? So to draw a picture of S of t as a summation, you can imagine that you have, okay, this is delta, another delta impulse at t, and yet another one at 2t, and so on, right? So that's what we mean by summing up a sequence of impulse, an infinite sequence of impulses at integer multiple of t. Let me just extend my drawing for a little more, give you a little more, a few more spikes right here. Okay, minus 2t, minus 3t, and the spike train extends to on both sides to infinity. A train of spikes, if you will, spikes, 知道吗 ？spikes 啊，刺刺的东西 spikes 啊。All right, so it's a train of spikes denoted as a summation of delta functions, shifted to the right and to the left. So this is S of t. Yeah. And then we also define something like this. We define the product. Just multiply our signal with S of t, and the result will be denoted as X sub S. Okay, X sub S. Yeah. So what does that mean? Knowing that delta t has this definition like spikes, so what we are going to do is to consider now, well, if S of t is like that, and if our signal is like this, let's say this is our signal, okay? So let's say this is our signal, and the signal is denoted as xc, right? Our continuous time signal, everything is still in continuous time, conceptually, right? So now, everything is still in continuous time, and we are going to multiply the two of them. We multiply our signal with the spike train, okay? With a train of spikes. What will happen? What will happen? So the result, at least in the time domain, is going to be change of the height of the spike, okay? We're going to change the length of the spike by our waveform, okay? So result, naturally, I hope it makes sense, will be a spike, but at a height that is modulated by the amplitude of our signal. So the result is going to be like this. And we just conceptually, we say that everything is still in the time domain, in the continuous time domain. Yeah. Okay? Can we agree on this? So this is a sketch of the result of multiplying the two of them. Okay? So X of C, our signal being in white, the white line is our signal originally. And now the yellow one, also a train of spikes, but each with different height, 高度不一样, but each with different height, and possibly also the polarity, 极性也不一样, each changing its polarity and height according to the amplitude of our signal. So that's a result of multiplying our signal with the S of t. Okay? And we're going to denote this result as X sub S. And why do we do that? Okay? So I said in this slide, we are going to, this is a preparation to explain the effect of sampling in the frequency domain. So as a step for preparation, we introduce this definition, x sub s of t. And the reason is because we argue this train of spikes with change in amplitude and polarity, it is a representation of sampling, right? If you look on the right, what is sampling? What's going on for sampling? Sampling is to take a measurement of our signal, and now the result is a train of spikes, if you will, each with different height, right? And possibly also changing polarity. If this goes negative, right, the polarity will change over there. But basically, we are modulating the height of a train of spikes by the amplitude of our signal. That's what's happening. That's another interpretation for sampling, right? So we argue that this is exactly identical. The only difference is that we draw an arrow. The only difference really is we draw arrows instead of, if you will, circles over here. Here we draw dots. We draw dots over here, fill circle, if you will. But then over there we draw arrows. 就画箭头. But otherwise the two are equivalent. Can we agree on that? This and that. Just the action of sampling, by definition, is the same as multiplying our signal with a train of spikes. A train of delta functions shifted to the right, to the left. Then we modulate the amplitude accordingly. Okay, so they are equivalent. But it turns out that it's more convenient to discuss the Fourier transform using this notation. Okay, so that's why this is how we prepare for a discussion. Okay, now we are prepared. Now we are prepared for the discussion of what's going to happen in the frequency domain. Is that clear? Yeah. So next thing, so if you agree with me that these two are equivalent to different interpretations, then we can now review the definition of Fourier transform for continuous time signals. Okay? The Fourier transform in this textbook has this notation. Okay? If any signal x, when we transform the signal and we denote the transform by script 草写, by script f, 草写的 f, the Fourier transform of our signal is a spectrum in the frequency domain. And the notation, let me introduce slowly. The notation is that they are going to form a Fourier transform pair, small x, big X. Is that clear? In this course, we use we use lowercase letters, 小写的, we use lowercase letters for time domain signals, and uppercase for frequency domain. Okay? Small x for time, big X for frequency. And we also use big omega for the frequency variable. Then with this, then the definition, mathematical definition for a transform is listed on the right. So here is written on the right. We are going to multiply our signal with e to the minus j omega t. Multiply them and then take an integral. The result is a function of omega. Is that clear? Yeah, so I hope this sounds familiar to you, brings you back some memory. You have taken signal and systems. Okay? And the integral runs from minus infinity to infinity for continuous time for a transform. Okay, so any question regarding the definition of Fourier transform and the notation? The notation, right. All right, so just to make sure that we are on the same, we have the same notations. Here, j is square root of -1. J is I. Okay. Somehow in EE department, we use j more than we use I. Yeah. Okay, so in this course, we use j for square root of -1. And e to the j theta, now you should be familiar that is e equals to cosine theta plus j sine theta. And here we have big omega denoting the frequency variable. And what's the unit? The unit of big omega, strictly speaking, is radian per second. A radian per second. if it appears in the power right here, 在指数的地方啊 it appears in the power right there. So e to the j omega t is going to be periodic, right? The frequency is exactly omega divided by 2 pi. That's the frequency. And the frequency unit will be hertz. Okay, so just to make sure that everything agrees with everything else, that's the notation we're going to use. Also your unit, okay, for you to pay attention. So with that, we call the result a spectrum. Okay, so I call x, this big X, the spectrum of our signal x of t. Big X, the spectrum, small x, the signal. Okay, so everybody okay with the notation? Yeah, maybe yeah. So hope that that's okay. But let me just write down the copy this notation in case we need it. Okay, f of x of t is gonna be denoted as big X with variable j omega, and the definition really is to take the integration from minus infinity to infinity, x of t inner product with that, and taking the integral, the t becomes a dummy variable, and the result is a function of big omega. Yeah. All right, so that's a bit about the equivalence of sampling as if we are multiplying our signal with a spike train, and also introduction, a review on the notation and definition of Fourier transform and what's going to be happening next. Next, we are going to discuss what's going on when we do this action, okay? When we define sampling as if we are multiplying our signal with the train of spikes. This is a multiplication in the time domain. But then the question is, what will happen in the frequency domain? Okay? What will happen in the frequency domain? Xc has a spectrum we are going to denote as big Xc. Okay? That's a notation. And if you will, S of t will have a spectrum that we can denote as big S of in the frequency domain. So in the next slide, we are going to go slowly, okay? Hopefully we can finish this derivation. So we are going to see what's going on when we multiply these two signals in the time domain. And then take the Fourier transform. Right? And then take the Fourier transform. I think I can probably erase things over there. Okay, so but take a look. So this equation derivation could be quite tricky. So let me first take you through. There are only like 5 equalities, right? 只有5个等式嘛. Yeah. The first thing first. So recall that S is a train of spikes, summation being summed over the dummy index of n. Okay. And just let me also mention slowly that whenever we have a summation, if I do not specify the range of summation, that means by default we are going to sum up from minus infinity to infinity. Okay, that's my notation. Okay, to be sort of sloppy. So using sloppy. Allow me to be sloppy whenever the range is not indicated. That means summation from minus infinity to infinity. Okay. So here we have S of t as a spike train, and it turns out that, okay, somewhat surprisingly, if you have an encounter, this is a somewhat surprising result that it's Fourier transform. The Fourier transform of this signal looks like itself. Okay, the result is also a summation of spikes in the frequency domain. Now in the frequency domain, what's going on here? So that means if S has a spacing, S being the spike train in the time domain with a spacing of t, then when we go to the frequency domain, it looks like itself, it resembles itself, but the spacing is now becomes inversely proportional. The spacing in the frequency domain is going to be 2 pi divided by t. That's the spacing. And now the domain variable is denoted as k. Okay, so we're going to sum up spikes in the frequency domain. The result is a spectrum. Okay, it's a Fourier transform of our spike train in the time domain. Right, the result is a spectrum, but it has this expression. It's a summation of impulses in the frequency domain. Somewhat surprising result. Okay, but now the spacing is inversely proportional to t. Okay, so let's try to draw a picture right here. So now after Fourier transform, now things are in the frequency domain, big omega, right? But now the spacing, we have the DC at frequency 0 for sure. But then with the spacing equaling 2 pi divided by t, we have the next spike on the right. We have the next spike on the left with also the same spacing. Okay? Same spacing, going to negative frequency and positive frequency. Okay? That's how Fourier transform works. So the spacing becomes inversely proportional with, so if we denote this as omega s, then this is 2 times the sort of the spacing. Yeah. So we define 2 pi over t. We define the spacing as big omega with this notation, this variable. Then now again, the result of Fourier transforming the spikes, the train of spikes, the result looks like itself. Only the spacing becomes inversely proportional. The more densely they are populated in the time domain, the more the broader they are apart. The more narrowly they're together in one domain, the more apart, more separated apart they are in the other domain. Inverse proportion. Okay, the spacing becomes inversely proportional. So that's the first thing to notice. And secondly, you need a sort of a normalization factor over there. So that's not super important. So I'm just going to, please trust me that we have this normalization factor right there. Okay. So this is one of the only few functions which preserves its shape after Fourier transform. I don't know if you have heard about this. There are only few functions that preserve its shape. 形状保持一致, preserves its shape after Fourier transform. This is one example. The other is Gaussian function. Okay, good student, right? Yeah, so kind of a good thing to know. But turns out that we are not going to, I am not going to use this directly. Okay, it's kind of cool to know, but if you will, so if you now look at this result, what we call big S, the spectrum, is a sum of spikes, right? But we also know what? What we know about spike what do we know about one spike? Every one spike in the frequency domain. What does it represent? Every one spike in the frequency domain represents a periodic signal, which can be written as e to the something t, something being its frequency, right? So just quickly, if the spectrum, if the Fourier transform is a sequence, an infinite sequence of spikes, then we know that back in the time domain, the signal can also be represented as a sum of complex exponentials, periodic signals. Every exponential j, this is the frequency, k times 2 pi divided by t. K times 2 pi divided by t right there. That's the correspondence. Okay? Every one component right here corresponds to one term in this summation. Now we are going back to the time domain. And this is quite tricky. This is the tricky part. This is really the tricky part. Okay? That I'm suggesting, okay, this is a suggestion, okay? I'm suggesting that you accept the equality holds. And this is quite tricky. Why? Because S is, we have already written the expression for S, right? S is nothing but this. But now I'm suggesting that maybe Yeah, I'm trying to convince you. I'm trying to convince to you that S of t can also be represented in terms of its Fourier series in time domain. Because each one of these terms, each one corresponds to one delta spike in the frequency domain. And I agree that I apologize. No, I acknowledge that this is the tricky part. That we are going to rewrite and use this expression. We are going to rewrite S of t, which is defined like that, as a sum of its Fourier series. This is Fourier series expansion, if you will. And that's the tricky part, okay? I think that's a really, really tricky part. Let me stop for a while, okay? Any comment? Yeah. Is anything that's not clear? Is everything clear? It's quite tricky. This equation is really the tricky part. It's also problematic. It is also problematic, but just bear with me. We are going to assume to be using this equality, okay? We're going to be using this identity, 这个恒等式, which might be problematic, but anyway, that's what I'm going to use next. Okay, yeah. All right, so yeah. So now, after I mentioned that this is a tricky part, yeah, just pretend that for time being, for a moment, we agree that this is real. This is true. Okay. For the moment, let's agree that this equality holds, and this is a good consequence. The consequence is that now we are able to talk about a Fourier transform of this guy right here. So this thing here is the result of multiplying our signal of interest. We're interested in knowing about this signal. So we multiply it with the spike train in the time domain, and then take the Fourier transform, right? But now the spike train can be rewritten as that. So why not just plug in this? Let's just substitute this expression into here, right? Fairly straightforward, right? We are going to substitute this expression in here. And we know that Fourier transform, everything's linear. So we can take the summation from the inside to the outside of Fourier transform. You can do that. Fourier transform is linear, a linear operation, linear transformation. Right? So take the summation outside as well as this scaling factor, which is not super important. Okay, take them out. Now in the inside, we have a summation of Fourier transforms. We have a summation of spectrums, if you will. And now, how about each term right here? We are going to sum over the index k. And each term now in the time domain, still in the time domain, each term has an expression of our signal multiplied or modulated with a periodic signal of frequency k times 2 pi divided by t, if you will, right? Because this is a frequency, right? This is sort of a modulation frequency. So far, so good? Just linearity of Fourier transform. Okay. So the second equality here is just linearity. Linearity of Fourier transform, right? Fairly simple, you can figure that out. But then the interesting thing here is that what's going on here? When we multiply a signal, when we modulate a signal with a carrier, using the terminology of in communication, when we multiply our signal in time with this complex periodic signal, complex exponential, if you will, then what's going to happen in the frequency domain? The spectrum will shift. This is the time that the moment that we can apply the shift theorem in Fourier transform. Okay? We multiply a signal. So this second equality, equation 2 right here, equation 3 right here. The equality right here at the bottom is a result of the shift theorem. The shift theorem. So each of the term, the summation is still there, but each of the term is a result of multiplying our signal in time with complex exponential, which is periodic, right? So we're going to shift the spectrum, entire spectrum of x to the right by so much, by k times this frequency, 2 pi divided by t. So that's a result of the shift theorem. So if you take note, shift theorem, that to say whenever we have a signal and we multiply it with a e to the j something, let's say omega naught t, a constant frequency, right? And you take the Fourier transform, the result is x, but shifted to the right by so much. Okay, the spectrum is going to shift to the right or to the left depending on the sign of the carrier frequency. That's a shift theorem of Fourier transform. Okay, now. All right, so that's a very brief derivation of what's going on when we multiply our signal with the spikes in the time domain. Yeah, over there. Over here. Multiplication of the time domain. It turns out that the spike train has a different expression which allows us to use the shift theorem to reach this conclusion that the spectrum of that, the spectrum is going to be a result of the original spectrum shifted to the right and to the left infinitely. There's going to be infinitely many copies of the spectrum, each shifting to an amount. In the frequency domain, we're going to sum them up. They all add together. They're all superposed. And again, this factor is not so important. Okay, the important thing is that they all add up. All the components are going to add up. Okay, so I think I can stop right here. Yeah. So tomorrow when we come back, let's make a sketch. Okay, let's continue this discussion of what's going on when we sample in the time domain. Okay, and the result is that in the frequency domain we have a few components, infinitely many components that add up. Okay, so tomorrow when we meet, we start with a sketch of what's going on. All right, so that's it for now. Thanks for sticking with me. See you tomorrow.